Can the people online hear me okay?
Yep.
Okay, cool. Yeah, so this is joint work with a neuroscience lab in the Netherlands. Us as a master's student, and Devika is the PI, and Dhruv Kohli is a PhD student here at UCSD, co-advised by Alex Cloninger and I. And this talk is about a new method that we've developed, which we call Riemannian alignment of tangent spaces, and conveniently that acronym is RATS. And this is a talk about decoding of neuronal manifolds. So in neuroscience, in the past decade or so, the paradigm has shifted from recording single units, single neurons, to being able to simultaneously record hundreds and thousands of neurons in animals that are awake and behaving and performing a task. And then we have these very large-scale data sets, hundreds of neurons, time series over hours and weeks and days, and animals learn and they sleep and they memorize things. So they needed new tools in order to analyze such data. And luckily, in the early 2000s, people developed manifold learning and dimensionality reduction techniques that allowed us to kind of reduce redundancies in large-scale data sets, visualize our data, and perform downstream analysis. So in neuroscience, a few years ago, one of the groups published a paper that had the word manifold in the title. Neuroscience Twitter kind of went crazy, hundreds and thousands of retweets. How dare they use jargon? We don't understand what a manifold is. But since then, many manifold learning papers and workshops have come up in the field. And one of the interesting aspects in this kind of work is that what we're looking at for neural activity is a lot of times it represents physical quantities. So it can represent timing, it can represent space. So in this case, for example, we have decoding from hippocampus in a navigation task. So there's a representation of space. In other cases, what we're looking at is the actual topology or geometry of the representation itself of the neuronal activity. And the thing that I've been concerned with is when we're looking at whether these neural populations, what are they encoding in terms of stimuli and the environment and the task, a lot of these dimensionality reduction manifold learning techniques have artifacts in them. So when we reduce from high dimensions to low dimensions, we introduce distortions. And then we want to be aware of what those distortions are when we're trying to determine what is the brain encoding. Is it not encoding because our method is performing poorly, or is it not encoding because it's encoding something else that we're not thinking of? So what is a manifold? Just very briefly, it's a topological space that locally resembles Euclidean space near each point, and in one dimension, this is a line or a circle, and in 2D, this is a plane, or the surface of a sphere, or the surface of a torus. And the example that I like to use a lot is the surface of the Earth is a manifold. And this idea of reducing dimensionality, visualizing data in lower dimensions comes up, for example, in cartography, where they want to take the sphere, they want to take the surface of the Earth, and they want to flatten it into a two-dimensional atlas. And this flattening introduces different distortions of distances and area and so on. And the cartographers can kind of be strategic about this in terms of what they want to preserve. Sorry, just realized that the Zoom panel is hiding my notes. And another thing that then can come up when we're considering manifold learning or visualizing our data in low dimensions has become popular in neuroscience and other biomedical fields is if you were given this two-dimensional atlas, how do you know if the source of the data is a three-dimensional sphere or ellipsoid of the Earth, or perhaps we all live on flat Earth? So manifold learning techniques can't answer this question, and this was one of the things that we set out to solve. So just briefly about manifold learning, the manifold assumption is that though our data is high dimensional, so every point is observed with a very large number of features, the data itself actually lies on the low dimensional manifold, so it doesn't necessarily need to be a linear representation. And with manifold learning, we're trying to recover this representation so we can do downstream analysis, so we can study the geometry of the data, and we want to do it in such a way that we're preserving geometric properties. And most methods in this field are what we are calling top-down. So they'll have some kind of initial global embedding of the data, a lot of times through some eigen decomposition, and then optionally they'll refine that embedding. So for example, here we have a UMAP embedding of the Swiss roll there at the top. So Swiss roll is a manifold learner's best friend. So they embed it in 2 dimensions. They have this weird step where they add noise to it, and then they iteratively refine it and try to unravel the Swiss roll. And what we're proposing is a bottom-up manifold learning framework. We're not the first to do this. And in this kind of framework, we are calculating local views with low distortion. So we first want to make sure for every point it has a good parameterization that has low distortion, and then we're going to solve an alignment problem stitching these views together in order to get a global embedding. So that's what we have here below from prior work, which we called low distortion local eigenmaps, and this talk is going to be about rats. So I'll explain the steps of these process. So one of the goals that we're setting out to achieve here is, again, if we consider, for example, a circle, its intrinsic dimension is 1. We only need the angle in order to encode where we are. But its embedding dimension is 2. We typically need 2 parameters in order to know where we are on the circle. Similarly, if we have a closed curve or if we're on the surface of the sphere. And what we wanted to know is what happens if you try to embed data in its intrinsic dimension. For example, you're a cartographer and you want to flatten the Earth into an atlas. And what happens if you take a sphere or a curved torus and you use common manifold learning techniques, I'm ignoring Mishne for a second and we'll come back to it, is that if you try to embed it in 2 dimensions, which is the intrinsic dimension, then you basically squash it. And the North Pole and the South Pole occupy the same space. So this introduces distortion. These points are very far away from one another in the data space and the ambient space, but they become very close to one another due to this squashing. So in bottom-up manifold learning, what we did in LDLE and what we're doing now, this should say in prep, but maybe we're done. In rats, we start out with data that we're assuming lies on a manifold, and then we find local neighborhoods of the data. For each local neighborhood, we now construct some low distortion local parameterization. And we do this in different ways in both techniques, using spectral approaches, and then taking into account the overlapping neighborhoods between these regions, we're able to stitch them together and form a global embedding of our data that is also low distortion. And one of the things that we enable in this technique is that we can tear a manifold apart so that we are embedding it in its intrinsic dimension, so that we are not squashing it, but rather we are tearing it and flattening it as we would an atlas of the Earth. So the way we do that is that we set up this global alignment problem so that we are trying to find orthogonal transformations, so rotations, of the points on the overlaps and translations, but only for points that are neighbors both in the ambient space and in the embedding space. So if points aren't neighbors in both, then we won't try to align them, and this is what automatically allows for a tearing of the manifold. So this, for example, is our sphere, and then iteratively we refine the global alignment so that we're able to tear it apart and embed it in 2 dimensions. And then I promised you that we'd be able to tell you if you're on the surface of the Earth or whether it's flat Earth. So we do this by what we call giving gluing instructions. So along the boundary of where we've torn the manifold, we provide a coloring that tells you, oh, these points are actually neighbors of these points, and these points are actually neighbors of these points, so we can kind of reconstruct what the original geometry was. So I promised to refer to Mishne earlier. So out of the methods that we compared to, Mishne is the only other method that sometimes, not all of the time, also tears manifolds, but in this case, we have no idea whether this was the original geometry of the space, whether it came from a sphere, whether it came from a circle. So we've torn our manifold apart. We want to be able to tell distances within this embedding. So for example, here we had points that were very close on the sphere. We tore in between them. And what we've defined then is what we're calling a tear-aware teleportation distance. So we're able to tell you that the distance between these 2 points isn't this red line, but rather what you need to do is go from yi to the boundary, you teleport over here, and then you go to yj. And this is similar to if you were sailing across the Pacific, then you don't drop off the face of the Earth, but rather you keep sailing along the other side of the map. So another question is now, how do you evaluate all of these low-dimensional embeddings? How do you know if you've done a good job? So most evaluation measures rely on local distortion. We developed 2 global distortion measures, as we're calling them. And what we're looking at is the distortions of paths in the ambient space and in the embedding space. So we're looking at whether paths are being contracted or expanded when we embed them from high dimensions to low dimensions, and we take maximum contraction times maximum expansion, and from this we get a global distortion. In the case of what we're calling weak distortion, what we're looking at are geodesic paths along the manifold, and then taking that same ordering of points of the geodesics from the data space, we look at that same ordering of points in the embedding. For strong distortion, we calculate our geodesics in both the embedding and the data separately. And I'm not going to show that here, but that actually leads to an interesting result on why repulsion, for those of you who are familiar with it, is a good idea when we do manifold learning. So this is one of the techniques in Mishne and UMAP. They have repulsions of points, and it actually naturally arises from this measure. And in terms of bounds on global distortion, so we have kind of an intuitive theorem. If the local distortions of your embedding, so the distortions of each local view are low, and the alignment error of stitching these together is also low, then the global distortion should be low too, and we can show this in the weak global distortion case. In the strong global distortion case, we have an additional condition, and then we can also show this when we tear the manifold apart, so using our teleportation distance. So since this is a talk about visualization, let's look at a few results. So we start out with a few synthetic data sets. So we're comparing different techniques. On the barbell, a square with 2 cutouts, and notice that they have different geometries, so you can see how these geometries get distorted by some techniques, and also a noisy Swiss roll, so how does noise impact dimensionality reduction? And on the right here, we have measures of global distortions comparing the different techniques to one another. So you can see that isomap, for example, kind of breaks under noise, as does LTSA, which is our nearest neighbor method-wise. And then Mishne, for those of you who are familiar, has this tendency sometimes to kind of tear things apart. So all of that was synthetic data. I promised you that this would be a talk about neuroscience, so let's move on to the neuroscience data. So this is a task developed in the Jazzieri lab. It's called a motor timing task. And what we have here is that the animal, in this case a monkey, is given 2 contexts, and it needs to indicate from the context how much time kind of needs to elapse, a slow time or a fast time. And then what we did was that we trained a recurrent neural network to recapitulate the same dynamics. So we give it the same kind of task. We see that the low-dimensional representations are similar. And in this, what this allows us to do, these animal experiments are very expensive and they're very hard to train. With the neural network, we can give it multiple types of context and kind of very densely sample a manifold. So the timing manifold, if you reduce it using PCA, we kind of get this curved manifold. And if we were to use nonlinear techniques in order to reduce the population activity, then we can see that Mishne and UMAP both introduce different types of distortions, whereas isomap and rats both reduce the dimensionality with very low global distortion. So those 2 are up here. And this is important because we want to be able to decode, for example, behavior and different measures from these manifolds. For example, here we're looking at the speeds along the manifold, and we can see that there's a very high fit between the speed along the manifold and the production time. So what is the time kind of the context from fast to slow? A more complicated task in this scenario, 1 minute to session end, okay. So a more complicated task in this case, the animal first needs to measure how much time has passed. So it has a ready cue, then there's a set cue, it needs to measure the time, and then there's a go cue in which it needs to reproduce that time, and we're looking at the estimation epoch. In this case, we can see both Mishne and UMAP introduce very high distortions, and with isomap and rats, there's much lower distortion, with rats having the lowest distortion. And then also we're able to show that these estimates follow a maximum likelihood estimation between the given timing of the interval and then the production timing of the recurrent neural network. So we can see that the population activity kind of behaves like a maximum likelihood estimate. So we have a few more synthetic data sets, and then we were also able to show this using real neuronal activity. So in a recent paper published this year, in grid cell population activity, they showed that grid cells, which are related to navigation, they have a toroidal-like topology. So this is again comparing, sorry, this got distorted apparently. Mishne, UMAP, something went wrong here with, it's supposed to be Mishne, UMAP, isomap, and rats. And what we do is we compare kind of these arrow diagrams that we have for the ideal torus to what we have for this grid cell population, and that tells us how to glue the data together in order to form a torus, and we indeed recover a torus. And similarly, in a head direction neuronal data set, basically head direction activity lies on a circle. We can tear the circle apart, and it's a one-dimensional manifold. So these are my collaborators. I'd like to thank our funding from NSF and NIH. And this is a neat illustration Dhruv produced of we can see the global alignment form over multiple iterations. That's it.
Thanks. Just one question in the interest of time. Does anyone have a question? Oh, okay. All right. The one question.
From the point of view of neuroscience, what does it mean that this surface has the shape of a torus? What does the topology mean here?
So it's actually a very strongly debated topic in the field of people studying navigation in neuroscience. The question is kind of what is the encodings of these cells, and do they encode for additional attributes of the environment? In this study, these cells were selected such that they were they were cherry-picked in such a way that, ta-da, there's a torus. For us, it was convenient because, ta-da, there's a torus. But yes, specifically, like that's a very hotly debated issue that I can discuss offline.
All right. Thank you, Gal. That was great.